Okay, start. So first, just to announce that we have these laboratory exercises on Wednesday this week, the second exercise of the first cycle, and we also have these recitations, these auditory exercises on Thursday at 4 p.m. Both will be organized using Teams, and assistant Branimir Dropulic will be responsible for these two activities. Now, what we have to do on our lecture today, it is the last topic that will be covered in this first cycle. And this last topic is related exactly to the laboratory exercise that you will be doing this Wednesday. It relates to linear prediction. This linear prediction is a very important tool in media coding, because many standards for video coding, for image coding, or for audio coding are based on predictive coding. And to understand what it means, we'll have to first introduce the theoretic background of this procedure, of linear prediction procedure. So the basic idea is the following. We are wanting to predict a scalar process y from a vector process x, capital X, caps X, bold. So this is the source which I'm using to do the prediction. And the target is the process y. This source has several components, not only one. So it is not 1 to 1, but many to 1. I have many components of the source process. And using these components, I want to predict what is the value for the target process y. And the assumption is that there exist certain statistical dependencies between individual components of the source process and target process y. Without these statistical correlations, without these statistical dependencies, it would not be possible to do the prediction. We will show later on that what are the necessary requirements in order to have the prediction gain. Predictor should be able to identify and model such statistical dependencies. And actually what we are doing, that by using such predictor, we are capable of describing target process y, in a simple manner. Most of the information about y is already contained in the source process that is used to create this prediction. And actually, what we have to encode is only the difference between the predicted value and the actual value. So it says here, only eventual differences between the predicted and the actual value of target y has to be encoded, has to be transmitted to the receiving side. Everything that can be predicted from x shall be predicted. It will not be transmitted as additional information. Okay? And what we have here is, let's assume we have a vector process, caps x, and this vector process consists of many such vectors, x1, x2 to xp. This p is dimension of this vector, so we have p components, x1, x2 up to xp. And these vectors are drawn from some distribution. So I have some distribution in p dimensions, and I take these random vectors from this distribution. And for each of these source vectors, I have the corresponding target scalar value. So for each source vector, I have the corresponding target value y. So this y is a scalar value, differently from the x, which is a vector value. Okay? And then the question is, can we predict y from x? And if we can, how accurate will be this prediction? In the actual application of this predictive coding, such prediction is always approximative. It is not exactly equal to the target value. And for that reason, we will introduce additional symbol. This epsilon tilde will denote the predicted value of target process y. So the predicted value is computed from the source vector. And the actual target value is y. And then the goal would be to have this y tilde as close as possible to the actual value of y. And of course, if I have only single source vector and single scalar target value, I can easily construct predictor that will be predicting this particular value from one vector, from one input vector. But I don't have only one pair, one source vector and one target scalar value. I have infinitely many such pairs. I have, let's say, 1,000 such vector and 1,000 corresponding target values. And I want to have the prediction that is as good as possible for all of those 1,000 pairs. Okay, so the goal of good prediction is that the prediction y tilde is as close as possible to the target process, and that actually means I want to minimize the prediction error. So this E is the difference between the actual target value and the predicted value, y minus y tilde. This is also a random process, because the source was a random process. It was a vector process. The source was a vector process. From this source, I have computed the prediction of the target. And this target is also a random scalar process. So all of the three are random processes. And if I have the difference, y minus y tilde, this E is then again a random process. So this E is a random process. And when I say it must be small value, it must be good prediction, I must introduce some kind of criteria that will be used to measure how good is this prediction. And typically, in practical applications, a simple Euclidean distance is used to measure this fitness, how good this prediction is. I simply compute the expected squared prediction error, the expected value of squared prediction error, or in other words, it is simply the variance of the prediction error. We also commonly use the terminology prediction residual. So this E is something that could not be predicted. It is something innovative, something coming out as a difference between the predicted value and the actual value. And for that reason, we call it prediction residual or prediction error. And this variance of such prediction residual or prediction error is a good measure of the fitness. How good is this predictor? I would like to have a predictor that has the least possible variance of prediction error. This expression for for the optimality of the prediction assumes that the predictor is also unbiased. And that means that the expected value of the prediction error is 0. So it means predicted value is always slightly above or slightly below the actual target value. But it is not consistently above or consistently below the target value. That would show that the prediction is biased. In our case, our prediction must be unbiased. So the expected value of the error must be 0. So I'm going either low or high, but not systematically high or systematically low. Okay? This predictor can be realized in different ways, depending on the type of statistical dependencies that we are trying to utilize. And most generally, this predictor can be constructed from the joint or conditional probability function between the source process and the target process. So the source vector process x caps x and the target process y, they have joint probability, they also have conditional probability density function. And this conditional probability density function describes these dependencies between individual components of the source vector and the target scalar value. However, in the actual applications, typically a simple linear prediction is used, and it utilizes the linear dependencies between source and target process, which are described through correlations. So instead of using a more general approach that is based on conditional probability, for the actual application, it is simplified by using a linear predictor, and this linear predictor can eliminate only linear correlations, linear dependencies between source and target process, which are actually correlations. So correlations are linear dependencies. More generally, this conditional probability can also describe non-linear dependencies between the source and the target. And in that sense, it is more capable of achieving higher gain for more general case, I would say. But in most practical application, we would use this linear predictor because it is much simpler. And this linear predictor, what it is actually a simple inner product between the source vector and the predictor coefficients. So this row vector alpha is the predictor composed of individual predictor coefficients, alpha 1, alpha 2, up to alpha p. And this row vector multiplies the column vector x, and this column vector is one of the vectors drawn from the source distribution. So I take one vector and I simply compute this inner product or scalar product. And this value is then the predicted value of target, y tilde. And our goal is to find the optimal values of this predictor, alpha 1 to alpha p. So to find the best possible predictor, I have to solve this minimization problem. I'm trying to find the coefficients alpha 1 to alpha p, which will minimize the variance of prediction residual. And this prediction residual, what is this sigma a squared? So this sigma e squared is simply the expected value of the difference between the target scalar value and the predicted value y minus y tilde squared. So I have this squared error, and I'm computing the expected squared error between the target and predicted target. And of course, it depends on the chosen predictor values, alpha 1, alpha 2, and up to alpha p. And then I'm trying to find the optimal solution for all of these predictor values, alpha 1 to alpha p, that would minimize this variance. Okay? It can be shown that predictor that fulfills this requirement, that is optimal in this sense. So the optimal predictor, minimizing this prediction variance, prediction error variance, must fulfill the following condition. It is also called orthogonality condition. And this orthogonality condition requires that the expected value of product of each source vector multiplied by corresponding prediction error. So each source vector has its own prediction error value. So the predictor error is the difference between y and y tilde. Okay? And then I'm requiring that this expected value of the product, source vector multiplied by the corresponding prediction error. This expected value must be a null vector. Only in this case, I have the optimality condition fulfilled. So it will really be the solution that minimizes the variance of the prediction residual variance. Okay? And this E, this error, is then y minus y tilde. It can be written as a row vector alpha times column vector x. But since this is a scalar value, I can also transpose this scalar value, so I can rewrite it as a row vector x multiplied by column vector alpha. It doesn't matter because it is the same thing. Okay, and then it says here that required condition actually implies that the prediction error must be linearly independent of each of the components of the source process. So this expectation means that each of the components of the source process, x1, x2, up to xp, each of the component is linearly independent of corresponding prediction error. Only in this case, the predictor is optimal, and we call this condition orthogonality condition. Okay? So if I take this value here for E, and if I substitute this E into this expression, expectation of column vector x multiplied by this scalar value. Okay, so expectation of x multiplied by this scalar value. I can rewrite this as a difference of two expectations, because the expectation is the linear operator. So this difference is a linear operator, and I can substitute the order of this subtraction and expectation, because the expected value of the difference is the difference of expected values. So I have the expectation of process x times target minus expectation of x transposed, x times x transposed times alpha. So expected values of the x process, so this is the vector of the process, source process, multiplied by the same vector but transposed, and multiplied by the vector of predictor values, alpha 1 to alpha p. So what is written here is also a vector. This is also a vector. It is not obvious from the first glance, because if I rewrite this, only this term here, this expectation of x times x transpose, it is the expectation of the column vector multiplied by row vector. What happens here, I have extracted the vector alpha out of this expectation, because the alpha is a constant vector. So it is just a set of constant values, alpha 1, alpha 2. It is not a random variable. The only random variable is x and y. So the vector x is a random variable, and the scalar value y is a random variable. So this alpha can be extracted to the right side of this expectation because it is a constant vector. So if I do this, I will start the notebook. Okay. So I have this expected value of x times y minus x transpose alpha. Okay? And then, as we said, we separate this into expected value of x times y minus expected value of x times x transpose times alpha. Okay, so this here is the expectation of a column vector x multiplied by a scalar value y. So altogether it is a column vector with p elements. Okay, the first part. The second part is, as I said, expectation of a column vector x, row vector x transposed, and multiplied by a column vector alpha. So this last term, this last product, this last factor can be extracted out of the expectation because it is a constant vector. So what is remaining within the expectation operator is simply this expectation of x times x transpose, and this is multiplied by alpha. This is multiplied by this vector alpha. Okay, now we will analyze in more detail what these two terms are. This term, this expected value of x times x transpose, and this here, the expected value of x times y. We will denote this with this here will be denoted with c xy, and this here will be denoted with phi xx. Just to understand what this outer product means. So this kind of structure is called outer product because instead, differently from the inner product, where I have a row times a column vector, now I have the column vector times a row vector. It is called outer product. And if I, for example, if I have such a case, I have x1, x2, x3, and I multiply this with the same vector but as a row vector. Then I simply apply the matrix multiplication rules. And it says I have to take the first row and multiply it with the first column. Okay, first row of the first matrix times first column of the second matrix. And that is x1, x1. Then I take the first row times second column. That is x1, x2. x1, x3. Okay, now I go with the second row. So I take x2 times x1, x2 times x2, x2 times x3, blah, 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 and finally the third row. x3, x1, x3, x2, x3, x3. What I get a matrix that is P by P matrix, and here it was a column with P elements and a row with P elements. So this outer product, x times x transpose, creates a matrix. And what I'm trying to find the expectation of such matrix. So I take all different vectors from the process, from the distribution of the source process. I take all of these vectors and I compute what is the expected value of such inner product matrix, and we will denote this matrix as phi xx, and this is also known as covariance matrix of the source process. Okay, next slide. So to find the optimal predictor, we have to solve a linear problem. On the left side, we have this phi xx times alpha. So I move this to the right side. What is left on the left side is then x times y. This x times y is this psi xy. So I have a linear problem. I have the covariance matrix phi xx that multiplies the row vector alpha 1 to alpha p equal column phi xy. So this psi xy is the correlation between each source component and the target process. You can see it here. So I take each source component, multiply by the corresponding target value. Okay, and that is the reason why it is a column vector. So the expected value of source vector x multiplied by a scalar value y. So this is p dimension column vector, and this is 1 by 1. This is scalar value. And for that reason, this expected value is a column vector with p elements. That is psi xy. Okay, so to find the solution, what I have to do, I have to invert this matrix phi xx. So alpha would be phi xx to the minus 1 multiplied by psi xy. So that is the optimal predictor. We will also put this bar here to denote the fact that this is the optimal solution for the linear predictor. The solution that minimizes the variance of prediction residual. Okay? It says here the solution is found as inverse covariance matrix phi xx multiplied by the correlation matrix psi xy, which describes linear correlation between target process y and individual components of the source process x1, x2 up to xp. Okay. This kind of linear regression, such problem is also known as a linear regression analysis or regression analysis. In the earliest form, this problem was known as least squares problem. So this linear regression is known as a least squares problem. And the method of least squares was developed by two mathematicians. One is Legendre. He published this idea in year 1805, and the other is well-known Gauss mathematician, and he published this idea in 1809. These are these two guys. On the left is this Adrien Marie Legendre, and on the right is Carl Friedrich Gauss. So they have independently developed this theory for finding the optimal least square solution. And why it was very interesting at that time, the problem that they were trying to solve, in the case of Gauss, he was trying to find the parameters of the trajectory of one dwarf planet, Ceres. So this dwarf planet Ceres had some kind of unpredictable trajectory when they measured with astronomical devices, with telescopes. And based on measurements, he wanted to estimate the parameters of this trajectory from the measurements. And then he used this least square solution to find the optimal parameters of the dwarf planet trajectory. And it was published in in a paper with a Latin title, and actually it was published only in 1809, but it was written in 1801, and for that reason the invention of the least square problem is usually attributed to Legendre, because it was published in 1805. Although this idea was also known by Gauss, and the solution was known 4 years before, but it was not published. And for that reason, they claim that Legendre is the one that introduced the method of least squares. Okay, then now we will discuss how to apply this linear prediction to prediction of time series. So I have a time series, and I want to apply the linear predictor to predict the next value of this time series from the preceding values. Okay? So the assumption is I want to model the time correlation of signal, so the correlation between individual samples of the signal, and I assume that the current signal sample, x of n, is correlated with the preceding samples, n minus 1, n minus 2, up to n minus p. So I said for real-world signals, there is a correlation between the current sample and preceding sample. One sample before, two samples before, up to p samples before. And if I know this correlation, if I estimate this correlation, then I will be able to predict what is the value of x of n from the values of the samples that I already have. So I already have samples x n minus 1, n minus 2, up to n minus p. Now the question is, can I use these previous samples to predict what will come in the current sample x of n? So as a real-world example, assume that this time series is a temperature measurement in each day. So I measure the ambient temperature at noon. And I have value for today, I have value from yesterday, from 2 days before. And now the question is, am I able to predict the temperature at noon today from the previous measurements from the previous days? Probably I could, but maybe this prediction would not be that accurate. But maybe in some case, if the weather does not change a lot, then probably the temperature today will be very much similar to the average temperature yesterday. And that is the reason that this linear prediction is a very powerful model that can be used to reduce the information, because everything that can be predicted shall not be transmitted. I only have to transmit what is new, what is the difference between the predicted value and the actual value. And I expect that this difference has a lower variance, lower information content than the original information without prediction. Okay? So the idea is that source process and the target process are formed in this way, from the same time sequence of signal. So I have a time series. The target is what? Is the current sample. Target is x of n. So this y scalar target value is the current sample at time index n. While preceding samples, xn minus 1, xn minus 2, up to xn minus p, are forming the source vector. So this is the source which I'm using to predict the target. Okay? If I want to depict this process of prediction, assume that this first plot shows the actual signal. The samples which are shown in red color from the index -5 up to index 4, these red samples are used to predict the current sample x of 5, the green sample. So I want to predict this value, x of 5, from x of 4, x of 3, x of 2, up to x of n minus 5. In this case, x of minus 5. How do I do this? I simply multiply each of these preceding sample with optimally chosen prediction coefficient. So I multiply this x of 4 with alpha 1, x of 3 with alpha 2, and then go to the last sample, x of minus 5. It will be multiplied by alpha p. In this case, p is equal to 10, so alpha 10. Then I simply add up all of these 10 products, and this will give the prediction of the current sample. So I will denote this prediction with x of n tilde. So this tilde again shows prediction of the actual value. So we see that if I apply the same predictor, but I simply shift it along this signal, I get the prediction for each position of the predictor relative to the signal. So the predicted value, x of 5, is shown here. It is close to the actual value, but not exactly equal. So now I can compute the error. What is the prediction error? It is the difference between the actual value, x of 5, minus the predicted value, x tilde of 5. And the last plot then shows the prediction error. So E of n is the difference between the target value, x of n, and predicted target, x tilde of n. And what I see is that this prediction error is of much smaller variance than the signal itself. So signal has large energy, large variance. On the other hand, the prediction is of much smaller variance. And we know that when we want to transmit something over a channel, this variance is very important, because the larger the variance is, I have to use larger number of bits, a larger entropy to encode this signal. Okay? The signal has larger entropy, and I have to use higher channel capacity to transmit the information. So by reducing the variance, I'm actually reducing the required channel rate to transmit the information about the signal. So I'm transmitting only the information about the prediction residual, or not about the prediction itself. Somehow I should be able to construct a prediction on the receiving side from the prediction residual. Okay, we will show later on how we actually do it. The proof that this is very powerful is shown here. So this plot shows a segment of a vowel. I think it is a vowel U. And this vowel, the solid line is the actual sample values, so the actual waveform, and the dotted line is the predicted value, where I use 10th order prediction. So I have computed such 10 values of the optimal predictor, and I'm simply applying this predictor to the last 10 samples of the signal. And I'm computing what is the current sample x of n from the 10 preceding values. And this prediction is shown with dotted line. And we see that the difference between the actual waveform and the predicted waveform is very small. So in the same scale, shown in the same scale, it has much lower variance than the signal itself. So if I'm able to transmit only this prediction residual as information, and if I'm able to reconstruct the original signal from the quantized prediction residual, I should be able to reduce the rate. I should achieve higher quality for the same rate, or lower rate for the same quality. Okay. So if I go back to the original expressions for the covariance matrix and for the column that describes correlation between the source and the target, now I can rewrite this equation, but by inserting the actual source vector. So in our case, the source vector is simply previous p samples of the input signal, xn minus 1 up to xn minus p. And we know that this phi xx, this covariance matrix, was the expected value of vector x multiplied by rho vector x transpose. So by inserting this source vector, this x of n minus 1 to x of n minus p, times the same vector as the rho vector, and by multiplying according to this rule of outer product, so I have this times this plot in the first row, first column. Then first row, second column, this times this, and so on. Then the second row, then the third row, and up to the last row. And the same thing is with the correlation column CXY that computes the correlation between each individual source component and the target. So the source components are xn minus 1 up to xn minus p, and the target is x of n. So again, in this case, the matrix is a column, a simple column with p elements. In this case, it was a matrix p by p. So with this phi xx is a covariance matrix, and this psi xy is this correlation column between the source and the target. And by actually rewriting the individual elements of the matrix phi xx and individual elements of the column psi xy, I can say that these individual elements in the ith row and kth column is what? It is the expected value of the product xn minus I, xn minus k. So if I compute this expected value, this is nothing else. I can approximate this expected value with a sample mean. So that is done in the practical situation where I don't have a known process with some PDF. I have only samples of this process. I have the finite realization of this process. And under assumption of ergodicity, so it says here, under assumption of ergodicity, instead of using the expectation, I can use sample mean to estimate the covariance matrix and to estimate the correlation column psi xy. This assumption of ergodicity, it says that the statistical properties of the process are present in a sample of a finite size. So it doesn't matter which finite sample I take from the process. I take, for example, 1,000 vectors randomly chosen from the process. And if the sample mean giving such covariance matrix estimate is the same or close to the actual expected value of this outer product, then we say that such process is ergodic. So process is ergodic if its statistical properties does not depend on the choice of the actual realization. So if I have sufficiently large number of vectors, let's say 1,000 vectors, and if I compute a sample mean instead of the expected value, so it approximates, this is the approximation of the expectation. And this approximation is valid if the process is ergodic. Okay? So instead of using the expectation, I use simply the average value of the sum xn minus I, xn minus k over all possible n's, so all possible time indices n for which I have the samples. The same here for the column psi xy. again, instead of the expectation, I substitute the expectation with the sample mean. So this is the estimate of the correlation column, and this estimate is valid if the process fulfills this ergodicity requirement. Okay. Finally, what I have is such a linear system of equation. So it is simply matrix P by P. This is the vector of unknowns, the optimal predictor coefficients alpha 1 to alpha p. And this here is this correlation column between the source, each component of the source, and target. So each element here, this phi of A, comma k, is given with this equation. So this equation is also valid for the case of psi xy, because in this case we have this I equal to 1, 2 up to p, while k is equal to 0, because I have the correlation between xn minus 1 to xn, xn minus 2 to xn. So always k is 0. So for psi, you can see here this psi has xn minus I times xn minus 0. So for that reason, for the column psi, I also have the same form of the elements phi of I comma k, but this k is equal to 0. In the matrix, I have I and k, simply I is the row index and k is the column index. Okay? And if I compute these values from the actual time series, so I have this signal x of n for many samples, I compute the covariance matrix phi, I compute the correlation column psi. And by inverting the covariance matrix and by multiplying this phi to the power of minus 1 times psi, I get the optimal solution for the predictor. It says here this term 1 over n can be also ignored. Why? Because it is cancelled. It is present here in the average value for the covariance matrix, and this 1 over n is also present here in the column vector for the correlation between the source and the target. And for that reason, I shall not write this 1 over n on the left and the right side. I can cancel this term. So I have this final expression that tells me how to compute the optimal predictor based on the correlation coefficients, this phi I, k, they are also called correlation coefficients. Okay? Now we will make a break, and after break we will discuss how this is then utilized in the actual coding system. Okay, now we are, okay, 2 minutes beyond full time. Okay, then break. If you have any questions, please ask. can continue. So, it says here, so once we solve this problem, once we find the optimal values for the prediction coefficients, predictor coefficients, we can use this optimal predictor to predict current sample from the preceding ones. Okay, as it says here, predictor with p coefficients can model the correlation up to p samples before the current sample. And this p is then called the prediction order. Prediction order, p, and the variance of the prediction residual is monotonically decreased by increasing the prediction order. So if I take not, for example, 2 previous samples, but 3 or 4 or 5, by increasing the number of preceding samples that I use as a source process to predict the current sample, necessarily the residual error variance is reduced. The implementation of the linear predictor is very simple. It is simply a digital filter that has a finite impulse response of order p, and whose its transfer function is denoted with p of z. P of z is the transfer function of the predictor. Okay, to compute the prediction, I have to apply, or I have to multiply pair factors, and I have to add them up together, so I have p minus 1 additions, and I have p multiplications for one output prediction. The block scheme is shown here. So this inner dotted system is p of z. So this is the predictor. The upper branch is simply a sequence of delay elements. So this z to the power of minus 1 is a filter state, or delay element by one sample. So if this here is x of n, then the output of this z to the minus 1 is x of n minus 1. Then this output of the second element is x of n minus 2. So it is just a delay line. I have p delayed samples, n minus 1, n minus 2, up to n minus p. And what I do, I multiply this one, x minus 1, I multiply it with alpha 1. So the first coefficient of the predictor multiplies the first preceding sample. Then the second preceding sample, xn minus 2, is multiplied by alpha 2. And blah, 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 up to the last one, xn minus p sample is multiplied by with the last predictor coefficient alpha p. And all of these products are add up together, and what we have, what results, is the prediction, x tilde. X tilde is the prediction of current sample x of n. And then if I subtract the prediction from the actual value of the current sample, what I get is the prediction residual or prediction error E of n. So altogether, if I take the output E of n as the output of a system, then such system is denoted as A of z. So its transfer function A of z includes also this difference between the input sample and the predicted value. But the inner system, P of z, only computes the output prediction. So this x tilde is the output of P of z, while E of n is the output of A of z. Okay, so then we can write here E of n is the difference between x of n and x tilde of n, and that is x of n minus this scalar product. So this here is nothing else but the inner product between the row vector and the column composed of p plus samples, n minus 1, n minus 2, up to n minus p. So it says here alpha 1 multiplied with x of n minus 1, alpha 2 with x n minus 2, and then up to alpha p x n minus p. So this here is the prediction. Okay, and if I now write the transfer function, so if I convert this difference equation into z domain, I can write what is the ratio of the z transform E of z divided with the z transform of x of z. Okay? So it is done according to the rules of z transformation, and this is, for example, if p would be equal to 2, then this E of n, the error, is x of n minus alpha 1 x n minus 1 e minus alpha 2 x n minus 2. So this here is minus x tilde of n. Okay? And then by applying the z transform, so this is then E of z, and this here is x of z. This here is minus alpha 1 z to the power of minus 1, because we have this delay by one step, x of z, and minus alpha 2 z to the power of minus 2, x of z. Now I can extract this x of z from the last three terms. So E of z is x of z multiplied by 1 minus alpha 1, z minus 1, minus alpha 2, z minus 2, okay? And then the ratio of the z transform of E and z transform of x is the transfer function of the system A of z. So that is the transfer function of this system that has the prediction error as output. So A of z is simply z transform of the prediction error divided by the z transform of the signal. And that is this term here. 1 minus alpha 1, z minus 1, minus alpha 2, z minus 2. Okay? And I can also write this is here minus p of z. So this here is a transfer function of the predictor. So this A of z is nothing else but 1 minus p of z. So the predictor, its transfer function is then p of z, simply sum alpha e z minus I from 1 to p. So this is the transfer function of the predictor. Okay, so now we have all the elements. We will denote this as a predictor transfer function, and this A of z would be the residual transfer function. Okay, and this E of z is the actual z transform of the prediction residual. Okay, now that I have this A of z, now I can also construct the so-called inverse filter, H of z. Why? Because as I said here, so the E of z, so the output of the prediction error. The prediction error is simply what? The prediction error is x of z times A of z. Okay? X of, so signal filtered by A of z. Okay? And if I want to get the signal back from this one, so I have the prediction error, and I want to reconstruct the signal from E of z. What I do, I have to take the reciprocal value. So if I multiply this E of z with 1 over A of z, and this would be denoted as H of z. So H of z is the inverse of A of z. So by simply multiplying this E of z with 1 over A of z, what I get is x of z. So I am able to reconstruct the original signal by inverse filtering of the prediction residual. Okay? So this inverse filter, it has transfer function, this h of z. H of z is nothing else but 1 over A of z, and this A of z was 1 minus P of z. Or written for the case P equal to 2, so this H of z was 1 minus alpha 1 z minus 1 minus alpha 2 z minus 2. So it is a second order recursive filter. It is infinite impulse response filter, IIR filter. IIR filter, in this case, is second order because P is equal to 2. So the order of this IIR filter is equal to the prediction order. So what I have the possibility to reconstruct the original signal. So the idea is the following. I start from signal x of z, and I pass this signal through filter A of z, to the filter A of z, which is equal to 1 minus P of z. Okay? And at the output of this filter, what I have, so this is in time domain x of n. And this output I have E of n. So then I take this E of n. Later on, I will have the quantizer here, quantizer. So this will be E quantized of n. And what I do, I simply pass it to the filter that is reciprocal. It is inverse to the A of z. So if I put here H of z, what is nothing else but 1 over A of z, I have here x hat of n, some approximation of the original signal that is, of course, not equal to the original signal. It will be equal only in the case that the quantization error is 0. So if this quantization is infinitely accurate, so if I have infinite precision, in this case, these two filters cancel each other, because this H of z is simply the reciprocal of A of z. And this here is cancelled, and I have that this reconstruction is identically equal to the original signal. So that is the reason usually this A of z is denoted as the inverse filter. Why? Because it is inverse to the H of z. It is only the issue of terminology. So this A of z, the filter that has the prediction error at its output, it is denoted as an inverse filter. So what it does, it computes the prediction residual from the input signal. And then by passing this quantized prediction residual through H of z, I get the approximation of the original signal. So it says here filter A of z and H of z are inverse one to the other. And in this case, zeros of A of z, zeros of H of z are the same as poles of H of z. So this A of z is a FIR filter. So it has finite impulse response, FIR filter. And this filter is described with zeros. So I can also rewrite this transfer function A of z which is simply 1 minus alpha 1, z minus 1 minus alpha 2, z minus 2, blah, 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 up to minus alpha p, z minus p, I can express this transfer function as a product of root factors. 1 minus z1, z minus 1. 1 minus z2, z minus 1. Blah, 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 blah. 1 minus zp, z minus 1. In the case that these roots are unique of the first order, then I have this root factor expression. The first term would be 0, 1, once z is equal to z1. The second factor would be 0 if z is equal to z2. So this z1 to zp, they are called zeros of LZ. But this polynomial is exactly the one in the denominator of h of z. So zeros in the denominator are actually poles of h of z. And that is the reason why I have to ensure that these zeros are not anywhere in the z-plane. They must be within the unit circle. Why? Because otherwise, if the pole is outside the unit circle, then the corresponding IIR filter, h of z, would be unstable. So in order to have the stable reconstruction filter, the necessary condition is that absolute value of each of these roots, z1, z2, blah, 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 must be less or equal to 1. So it means up to zp. So all roots of the transfer function a of z, or denominator of the transfer function h of z, all these roots, they have to be within the unit circle. So, for example, if this is the unit circle in the z plane, so this is the z plane, I can have a pair of conjugate complex roots z1, conjugate complex, z1 asterisk star. I can have another pair here, z2, and z2 asterisk, okay? But there should not be a root that is outside this unit circle. So this here is unity 1. This here is 1, okay? Because if I have any root that is outside the unit circle, for example, this one, z3, this is the unstable pair. So I have to find a solution for the predictor that has all of its roots within the unit circle. Only in this case, the inverse filter, h of z, is a stable filter. Otherwise, what it means that it's unstable. It means that although I have the finite excitation of the reconstruction filter, what happens is its output is exponentially increased with time. So it is behaving something like this. Okay, so this is the output of an unstable system. So although the excitation is finite, or finite energy, the output goes to infinity with exponentially increasing value. Okay? And that is the reason why it is necessary to have a solution where all the roots are within the unit circle. In that case, also the reconstruction filter is a stable filter. Okay? And one possible solution to ensure this is to apply the so-called autocorrelation algorithm to compute the solution. this autocorrelation method or autocorrelation algorithm defines the correlation coefficients in a slightly different way. So if you compare this original matrix equation, so I had this correlation terms phi I k, which were simply sum 1 over n, xn minus I, xn minus k. Okay? And now, instead of using this more general term, I will introduce another linear system of equation where these matrix elements are bounded to only given values. For example, phi a comma k would be equal to r of absolute value I minus k. What is r? R is the autocorrelation value, autocorrelation coefficient, which is defined according to this expression here. Autocorrelation for value j is simply sum from 0 to n minus 1 minus j, x of n plus or minus j, doesn't matter, n plus j. Okay? So this here is denoted as an autocorrelation. So what I take only the absolute difference between index I and k, and I compute the autocorrelation window value for lag. We call this lag. So this is this delay. How much I delay one of the sequence. I delay it by j. So if j is equal to 0, it is nothing else but the sum of squared values of x of n over the window of length n. But if j is equal to 1, then it is the average of a product xn plus 1. So I take the correlation between two neighboring samples. And I average this, I average it over n samples, but this averaging is not necessary because this 1 over n is cancelled in the left side and on the right side of the matrix equation. So the element of the matrix, this element is then, instead of phi of I comma k, I have r of absolute value I minus j, I comma k, I minus k. So here it was 1, 1. So row index I, column index k, okay? 1, 1. Then here it was 2, 2. Here 3, 3, blah, blah. Then for all of these values on the main diagonal, what I have I minus k is equal to 0. Okay? And then I have r of 0 on the main diagonal of the covariance matrix. This will be called autocorrelation matrix. So r of 0 is on the main diagonal because row and column index are the same. Then again, here, the first auxiliary upper diagonal or first auxiliary lower diagonal, they have the value r of 1 because the difference between I and k is 1. So this here is 1, 2, or this here was 2, 1. In both cases, I have the difference that is equal to 1. Absolute difference is equal to 1. So for that reason, I have r of 1 on the first lower diagonal and on the first upper diagonal. Okay, r of 1. Sorry. And then the same principle is applied here. R of 2, R of 3, R of 4, blah, blah, up to R of p minus 1. So the last element, it was first row, column p, and the difference is p minus 1. The same here, it was row p and the first column p minus 1. So the elements in the matrix phi xx, these elements are completely described with only p different autocorrelation values. I have to compute the autocorrelation with leg 0, with leg 1, with leg 2, up to leg p minus 1. So now I have defined the whole autocorrelation matrix phi xx. Now what I have to compute this correlation column xy, and this correlation column, we know that it was phi I comma 0. So this psi xy was phi I comma 0. So k was 0. And this means it is equal to r of a, because the absolute difference between I and 0 is I, and this column is then r of 1, r of 2, r of 3, up to r of p. This here is the same value as this one, r of 1 on the first auxiliary upper and lower diagonal, and this value, the last value, r of p, is only here, it is not present in the matrix. So in the matrix we have the values r of 0 to r of p minus 1, and in the correlation column we have the values r of 1 to r of p. So actually what we have to do, we have to compute these autocorrelation values from the signal, but only for these p plus 1 values, from r0 to rp. R0 is a special case. It is nothing else but the sum of squared values of x of n from 0 to n minus 1. Then, for example, R01 is then sum of products from 0 to n minus 2, x of n plus 1. So I take the average correlation between two neighboring samples, and so on up to r of p. Okay, now that I have this system of equation, I find the optimal solution, and this optimal solution that is found with this autocorrelation method will always have stable predictor. Actually, the solution with the autocorrelation method will always give a predictor whose roots are within the unit circle. So its module absolute value is less than 1, less than unity, and this ensures the reconstruction filter to be stable. So the inverse filter A of z, all of its roots, they are also the poles of the edge of z, and all of these roots are within the unit circle. Okay. Due to a very high efficiency of prediction for many natural or real-world processes and signals, the linear prediction procedure is oftenly applied in media signal coding. And algorithms that use the linear prediction, they are commonly denoted as linear prediction coding algorithms, or LPC. The abbreviation of this method is LPC. One of the first applications of this linear prediction coding was exactly for speech signal coding, for coding of speech. Later on, it was applied to other media signals as well. And there are two basic architectures how this predictive coding can be applied. How can be applied for the rate reduction. So our goal is how to apply this prediction to reduce the required rate for transmission of media signal. One possibility is open loop prediction. So it is called coding in open loop. Or the other way is closed loop prediction. And the main difference is what is the source that is used to compute the prediction. So what is the process X that is used to compute the prediction? In the open loop case, it is the original process. So for the first approach, open loop coding, or coding using open loop prediction, the source for the prediction computation is the original process. On the other hand, if I apply the closed loop approach, then instead of using the original process, I will use something that is available on both sides, on the predictor or on the transmitting and receiving side. And what is this? This is actually the quantized reconstructed process. So quantized reconstructed signal is close to the original signal. It will be clear when I explain this block diagram. Okay? So this here is the open loop approach, open loop configuration. I start from the original signal. I compute the prediction, x tilde of n. I subtract the prediction, I get the prediction residual. It is the same as I have shown here. Okay? It is the same one shown here. So I take original signal, I compute the prediction, I subtract the prediction from the original signal, and I have the prediction residual, E of n. This E of n is then quantized. So this quantization is performed with a lower bit rate, or the entropy of E of n is smaller than the entropy of x of n. And that is the reason, that is the basic source for rate reduction. So instead of quantizing the original signal that has higher entropy, I am quantizing the prediction residual, which has lower entropy. And I can encode this signal with the same quality, but with much lower rate than the original signal. So this here is the quantized prediction residual. And then I apply the inverse of this filter. So this is the A of z filter, and this here is H of z filter, which is nothing else but 1 over A of z. So it has the feedback loop. So this here was feeds forward, so it was only FIR filter. It had only delay elements, and I combined these delay elements to compute the prediction. I subtract the prediction from the original signal. I have the prediction residual. But now I have the feedback here. So I take the output signal and I feed the predictor from the quantized, from the reconstructed signal. And for that reason, this prediction here is not equal to the prediction on the transmitting side. Why? Because the x hat is only the approximation of x. It is close, but not equal. For that reason, if I use the same predictor, but on different source, I have different result. So this prediction is close to the original prediction, but not equal. Why not equal? Because the source of the prediction is not the same. Here it was x hat, and here it was x of n. So due to different source used for the prediction on the transmitting and on the receiving side, I have additional error. So this additional error is then combined with the quantization error. So if this would be the same as this one, then the difference between x of n and x hat will be equal to the difference between E and E hat. So if these two are the same, what I subtract here, I simply add up back here. And the only difference between this line and this line is the difference due to quantization, difference between E and E hat. But if these two are not equal, and in the case of open loop quantization, they're not equal. Why? Because the source is different. The source used for computation of prediction is different here and different here. Then this difference is additional source of error. So the error is combined quantization error and the prediction difference error. Okay? But nevertheless, this also works. Don't be fooled. So it's also very useful in this open loop configuration. In the actual laboratory exercise, you will compare what is the behavior of such system that uses this open loop configuration for prediction and later on for reconstruction. Or the other way is to have a closed loop approach. And closed loop approach is shown with this block diagram. What I do, I simply make another replica of the reconstruction site. So this is a local reconstruction unit that is a part of the transmitting site. So this here is only used for one reason, and that is to ensure that this prediction is the same on both sides, on transmitting side and receiving side. So this here is this remote decoder. This lower part is remote decoder. It takes the quantized prediction residual on its input. So this input is quantized E of n, E hat of n. So this here is the same as the one before. This here is just repeated in the lower part of this image, okay? And this here is again repeated here. It is like a local replica of the decoder, but on the encoding side. So this upper part of the image is the transmitter, and this lower part of the image is the receiver. Now this here is simply replicated on the transmitting side. Why? Only to compute x hat of n from the same source, only to compute x tilde of n from the same source, and source is x hat of n. So I do the reconstruction on the transmitting side. I compute the x hat, the reconstructed signal value, or the quantized signal, and I use this quantized signal as a prediction source to compute the prediction, x tilde. And then I use this x tilde and subtract such prediction from the input signal to get the prediction residual. This prediction residual is quantized. I get E hat, and this E hat is then transmitted both to the local replica of the decoder and to the remote decoder. They are the same. And for that reason, this x hat and this x hat, they must be the same, because they are based on the same quantized prediction residual. They are initialized the same, and they are fed with the same input signal. For that reason, their output must be the same. And then, since both encoder and decoder, they have the same prediction, now I don't have the error that was present here. So this error, due to the difference between two different predictions, is now zero. Is zero, because both predictions are the same. So this x tilde, this x tilde, they are the same. And whatever I subtract here, I add up here. So this x tilde is simply cancelled. I subtract it here, and I return it back on the receiving side. And in this configuration is called predictive coding in closed loop. With such a configuration, I have only one source of error. And this is the difference between the original prediction residual and quantized prediction residual. This E of n minus E hat of n, this difference, quantization error, that is the only error between x of n and x hat of n. So the complete behavior of the system is described by the behavior of the quantizer of the prediction residual. Okay? Then one additional topic is related to the adaptation of the prediction filter. As I have said before, so this predictor must be optimally determined. And one possibility how to determine the predictor is with a linear prediction autocorrelation method for linear prediction coding. So this is one possibility how to compute the optimal predictor for the given input signal. But of course, this is only in the case if the statistical properties or correlation properties of the signal are unchanged. So if this signal has the same correlation properties, then I have only one possible optimal solution for the prediction, for the optimal predictor. But speech signal or any other media signal is not such signal where the correlation properties are constant, but they are changing. And for that reason, I have to change the predictor coefficients from time to time. I have to recompute the optimal values of the predictor. And of course, I have to somehow transmit to the receiving side what are the optimal values for this given part of the signal. So, for example, if I'm pronouncing a word with a sequence of 3 phonemes, whatever, cat, so this part of the word k of cat is different from e or from t, from the middle part or from the last part of the word. And for that reason, I have to change the properties of the predictor. I have to change the values of the most optimal predictor for the k part, for the e part, and for the t part of the cat. And this information can be sent as a side information from the transmitter to the receiver. So I simply adapt the predictor from time to time. For example, 50 times in second, I send a new predictor coefficient values. I compute the optimal predictor, and I somehow transmit to the receiving side what are the optimal values for the predictor alpha 1 to alpha p for this part of the signal. Okay, and just as an example for the actual speech coding algorithm that you use every day on your mobile phone, once you are speaking on one side, this linear prediction coding of speech is performed by computing the optimal predictor, typically 50 times per second or up to 100 times per second. So this linear problem of equation, 10 by 10 linear system of equation, is computed, the solution is computed either 50 times per second or 100 times per second while you are speaking. So as you are speaking, as you are uttering these vowels or consonants, so phonemes, the mobile phone is taking the segments of this speech signal and computing optimal predictor values for each such segment. And these segments are typically around 20 milliseconds long. So 20 to 30 milliseconds are these speech segments, and for each of these segments, the optimal solution is found and transmitted to the receiving side as a side information. So if it is transmitted as a side information, then it is called forward adaptation. So it says here there are two possible solutions. One solution is forward adaptive prediction, where I say, okay, for this block I will use this predictor, this set of predictor coefficients. So I will send this information as additional information beside the quantized prediction residual. The other way is backward adaptation. Backward adaptation, and that means that the optimal predictor is computed from the previous reconstructed signal. So I use the statistics where I compute the statistics, the correlation statistics from x hat. And based on this x hat, I will recompute the optimal prediction values for P of z on both sides. Since both sides, they have local replica of x hat or the remote replica of x hat, both sides can recompute or adapt the values of the prediction to the correlation properties of the signal. And that is okay as long as this x hat is close enough to the original x, and as long as these correlation properties are slowly changed, because this is always based on the previous statistics. So this x hat of n are previous time samples and previous correlation statistics. And on the other hand, I want to apply it for the block that comes from that point on. And for that reason, such backward adaptive adaptation of the prediction is suboptimal, because I use the previous correlation properties of the signal to adapt to the forthcoming part of the signal that will be encoded with this predictor. So it is suboptimal. In the forward adaptive, I will take the whole block of the signal, I will compute the optimal predictor for this block, and then I will send this information as additional information to the receiver, together with the indices of quantized prediction residuals. So that is then forward adaptive prediction. Okay. So what we have learned, what is the task of prediction, what is the predictor and how to compute it, what is a linear predictor, how to find the optimal solution, and what is the orthogonality condition, what is the least squares method and how it is related to this linear regression method, and how to model the time correlation by actually constructing a source process from the delayed samples of the time series. Then we have shown that this linear prediction can be applied for the correlated signals, and what are the properties and possible realization of the predictor. And the reconstruction, how this reconstruction can be done from the prediction residual, either in the closed loop or open loop approach. We have also shown how this autocorrelation method can be used to find the coefficients that ensure the stability of the reconstruction filter. Okay? And last, we have shown a little bit about the adaptation of the predictor, either forward adaptation or backward adaptation of the predictor. So now it's 3 minutes after 6. We'll make a break now. And after the break, we will show some basics about speech coding. Okay? Questions? Okay, so continuing. Now we will show how this linear prediction technique can be used to efficiently encode speech signal. So practically most of the speech coding nowadays is based on linear prediction. And the reason for this is that this linear prediction model is very close to the physical process, how the speech signal is obtained, how the speech signal is constructed. And that is the reason why this linear predictive coding is almost ideally suited for the speech signal. With speech signal, there are two main sources of correlation. One, the first part are the so-called short-time correlation, vremenski kratkotrajne, short-time correlation. They are related to the behavior or to the influence of the vocal tract on statistical properties of the output signal. So the correlation properties are determined exactly what is the shape of the vocal tract when you are pronouncing certain sound. So if I am pronouncing sound ah, then the shape of the vocal tract, so its cross-section area is changed along the main axis of this vocal tract in a given function. So this cross-sectional area is changed as some function of the position of the vocal tract. And this shape of the vocal tract determines what are the correlation properties of the output signal. And that is the reason why the vowel A is different from E, from E, from O. So the shape of the vocal tract is different. Differently from the short-term correlation, we have long-term correlations. And these are related to excitation of the vocal tract. This excitation is due to vibration of the vocal folds. So these glottis are, or vocal folds, they are vibrating in the airstream that passes from your lungs through this glottis area, through vocal folds, into the vocal tract. So this stream of air is being modulated on the vocal folds by opening and closing of this glottis. So this glottis is intermittently opened and closed, open and closed. And this happens with a frequency of approximately 50 hertz, maybe 60. These are very low frequencies for large male speakers. So male speakers that are very corpulent, so they are very high and very big mass. So they would also have a very low frequency of vibration of vocal cords. On the other hand, for female voices or for child voices, this frequency is much higher. It can be up to maybe 300 hertz. So from 50 or 60 hertz is the lowest fundamental frequency of the vocal cords vibration, up to maybe 200 or 300 hertz for very high-pitched female voices or for high-pitched child voices. And this correlation can be also utilized to achieve high efficiency of predictive coding. So both short-term correlation as well as long-term correlation, both can be utilized to achieve high coding efficiency. Okay? And now I will depict these long-term correlations. So this here is one pulse that is resulting from one opening and closure of the vocal folds. So this puff of air, after passing through vocal tract, at the output of the vocal tract I have certain waveform. And this waveform is repeated once the vocal folds are opened again and closed again. So for each opening and closing of vocal folds, I have one such output pulse at the output of the vocal tract. And obviously, this period is very much similar to this one and to this one. So I have some kind of long-term correlation, and this long-term correlation is with the period, with the time distance, let's say, with the lag of approximately 3 milliseconds for the highest pitch. So if the pitch is 300 hertz, then this lag, this time delay is 3.3 milliseconds. On the other hand, if it is a very low pitch male voice, like 50 hertz, then this time delay, this period is around 20 milliseconds. So very long period of correlation. Okay? These are long-term correlations due to periodicity of excitation for the case of voiced sounds. So only certain sounds are voiced sounds, others are unvoiced. For example, if I have the consonant B and P, one is voiced, the other is unvoiced. They are pronounced in a similar way, but the only difference, the main difference, is whether the vocal folds are vibrating or not. B, B, P. Actually, with B, it is vibrating case, so I have the periodic excitation. B, B, like a boot or boat or whatever. But if I have the corresponding pair, it's P, like pair or peer or whatever. So this P at the beginning is the unvoiced pair of B. And in this case, the vocal folds are not vibrating, and the excitation in the case of unvoiced sound is more or less like a random noise, as if the vocal tract is excited with a random noise signal. If the consonant is a voiced consonant, then the excitation is like a periodic excitation. Okay? So this is the case for this voiced sound, where I have the periodicity of the excitation signal, and this period, this basic or fundamental period, defines the lag, the delay between two neighboring periods. Now if I emphasize, if I magnify only this part of the signal, it is shown here. So if I magnify the time axis and show only this middle region, it is this kind of waveform. And I claim these 10 samples shown here are correlated with this one. So these are short-term correlation because it is close neighboring samples are correlated with the current sample. So I take 10 last samples from the speech signal, and I claim there is a correlation between these 10 samples and this sample that I'm predicting. This correlation is called short-term prediction or short-term correlation. Okay? So the long-term correlation are related to the excitation of the vocal tract, to the period of the glottal pulses, where each period corresponds to one opening and closure of the vocal tract, where a new pulse of the air stream passes through lungs, through glottis, through the vocal tract. And as I said, the period of this is between 3 milliseconds for very high-pitched female or child voices, up to maybe 12 to 15 milliseconds for very low-pitched male voices. Okay, and this long-term prediction is very successful, or very results in high rate reduction if there is a correlation between two neighboring periods. If two neighboring periods are very similar, then of course then the difference between this period and this period is very small. So I could have a high prediction gain if I quantize only the difference on this length. Okay? On the same thing, the same analogy is for the short-term correlation, where certain sounds that are correlated have higher prediction gain, other sounds that are maybe less correlated have a lower prediction gain. And that is based on how much these preceding samples are correlated with the current sample of the speech signal. This plot shows how successive periods of periodic speech are similar to each other. So if I would plot this period above this one, so if I plot them one above each other, then I see that all of these periods are more or less similar to each other, but I have certain variation in the actual value of the period. The period is not constant, but it is changing. Why? Because we have the natural pronunciation frequency, which is varying. So when I'm pronouncing speech sounds, I don't have constant pitch. So constant pitch would be so I'm trying to keep the frequency of the fundamental frequency of the vocal folds to be constant as much as possible. But with the normal pronunciation, this frequency always changes. And this envelope of the frequency is this prosodic information that we also use to convey the information whether the sentence was a question or some statement. Okay? If it is a question, what's the time? So this shape of this variation, pitch variation, is of one kind for this question type of sentence. And if it is a statement, it's 5 o'clock. So it is usually dropping at the end. If it is a statement, if it is a question, it is increasing. The pitch frequency is increasing at the end. And this variation of this pitch frequency is shown here. Okay, as I said, the short-term correlation are related to the vocal tract and to its shape. And these are limited to the periods of approximately 1 millisecond. So they are really close correlation. So only 1 milliseconds prior to the current sample, there is some correlation from this to that one. But if I go further, there isn't that strong correlation between samples that occurred maybe 5 milliseconds before, because they are then, in this case, long-term correlation related to periodicity of excitation. Short-term correlations are limited to only this period, maybe 1 millisecond prior to the current sample. Okay? Short-term correlation. And this short-term correlation, it is due to the fact that the vocal tract behaves as a set of selective filters, which are emphasizing certain spectral regions of the signal. For example, this will be transfer function. So this is the amplitude characteristic. So amplitude transfer function for one vowel, maybe vowel A. So this is the vowel A. And when I'm pronouncing the vowel A, the transfer function of the vocal tract amplifies certain frequency regions with higher gain than the other. So maybe the region around 800 hertz is amplified. The region around 1.2 kilohertz is also amplified. Then in this part of the spectrum, I have a lower gain, so it is much less present in the output signal. Then again, at 2.4 kilohertz, I again have some kind of amplification. And this position of these resonant characteristics they are called formant characteristics. So these are formants. First formant, second formant, third formant, and they are characteristics for the actual sound that I am uttering, the actual sound that I am speaking, phoneme. So for vowel A, for vowel E, E, O, so they are different. They are shifting depending on the sound that I am uttering. Okay? These are called formants. First, second, third, and so on. And they are completely described through what? They are completely described through these coefficients here. This alpha 1, alpha 2, up to alpha p. So these coefficients of the predictor, which are also the coefficients of the denominator of the reconstruction filter. These coefficients are related to the position of these resonant characteristics. So I could easily compute from the actual values alpha 1 to alpha p where is this resonant characteristics? It is actually defined by roots. So this Z1 and Z1 conjugate complex is the first formant characteristics. I simply take the angle of this first root pair, this angle here, theta, and if I divide this angle by pi, and if I multiply it with half of the sampling rate, fs over 2, I will get the frequency in hertz, where this pair of poles would cause this kind of amplification. So I will have the gain of the amplitude function, amplitude transfer function, at certain frequency, where this first conjugate complex pair of poles is affecting the transfer function. So if I go from 0 up to 1/2 of the sampling rate along this unit circle, I will simply test how does the vocal tract affect the output amplitude. And as I come close to the pair of poles, then this amplitude increases. Then I come close to these two conjugate pair, then again the amplitude increases. So something like this. So as I come close to the pole pair, then I get this formant characteristics that is shown here. And for each sound that I'm producing, these formants are different. And even so, with different speakers, they are different. So if I would pronounce all 5 vowels in Croatian, a, e, I, o, u, e, this is the 6th neutral vowel. Then if the colleague would produce the same 6 vowels, then the formant frequencies would be slightly different. So the identity of the speaker is also encoded in the position of these formants. So not only position, but also these bandwidths. For some person, this bandwidth is narrower. For some person, it will be wider. Okay? These are the formats. Then speech spectrogram. It shows how the spectrum is changed with time. So in this case, this speech spectrogram, it has time axis here. It has frequency axis here. And what I see here is the periodic behavior of the spectrum along the frequency axis in the part where I have the periodic excitation for the voice speech. So this here is the vowel A, because I have pronounced sa. So the first part is the consonant S, which is unvoiced, and the second part is the vowel A, which is voiced vowel. And what we have this periodicity. The amplitude is shown with the color. Okay, so this is the time axis, this is the frequency axis, and this amplitude, so how high I am, is shown with the color in decibels. So this red is very high, blue is very low. Okay, and now I see individual harmonics for this periodic signal. And I see that this frequency is not constant. It is harmonically related, but it has this varying envelope, varying shape. And this varying shape is due to this natural intonation, that I change the fundamental frequency along this pronunciation of this sound. Okay, that is called narrow band spectrogram, uskopojasni narrow band spectrogram. Why? Because now I can observe individual harmonics of speech signal. But some of these harmonics are of higher amplitude, some other are of lower amplitude. Why? Because the spectrum is filtered with the transfer function of the vocal tract. So harmonics that are falling in this region are amplified, harmonics falling in this region are attenuated. Okay? If I use wide band spectrogram, not narrow band, but wide band, then I would get exactly these ridges, how this formants are distributed along the spectral domain. So if I use this wideband spectrogram, then I would show exactly the position of the first formant, the second formant, third and fourth, while the position of individual harmonics is not shown anymore. So that is the reason the signal is the same. Signal is the same, but only the processing is different. The time window is different. If the time window is wide, then I would get the individual harmonics. I would get the narrowband spectrogram. If the time window is narrow, I would get a wideband spectrogram that shows the formant structure. It shows position of first formant, second formant, third formant, and fourth formant. Okay? We also see that the formant frequencies are also changing slightly during pronunciation. So with this sa, I have the varying first formant, varying second formant. So they also have some curve, some function, some time dependence. Okay? Now going to the history of modeling of speech, we can say that research in the speech area began very early. The theory or modeling of encoding of speech, they are based on the results of physicists, and engineers already from the 18th century, because they analyzed and introduced different physical models for generation of speech, for speech generation in vocal tract. And they have built different mechanical and electrical models, devices. They were trying to imitate the process behaving in the actual vocal tract to synthesize speech. And one of such early investigators was this Wolfgang von Kempelen. This Wolfgang von Kempelen, he was originally from Hungary. He lived from 1734 to 1804, and in 1791 he built mechanical instrument that was able to reproduce or to simulate speech. And it was described in one book, Mechanismus der menschlichen Sprache, nebst Beschreibung einer sprechenden Maschine. And these are the plots from this book that describe how to construct such mechanical model for speech production. This here would, this bellows would imitate the lungs. So I have some pressure here, and it will create constant airstream, and this constant airstream is then passed through a reed. So this reed is like a reed instruments where you have this vibrating piece of wood that vibrates in this airstream and creates this periodic excitation, periodic sound. And then this part here is trying to change the cross-sectional area that models the vocal tract. And it was controlled with your hand. So you would put your hand through this hole and somehow change the shape of this area to get different sound. Okay? And this is the actual original model that is currently in the exhibition of Naturwissenschaftsmuseum für Technik in Munich. And this is the original model built by this guy, Wolfgang von Kempelen. You see this, some kind of levers that were used to control the pronunciation of individual sounds. And these here are these bellows that are pressed to create this airstream passing through this model of vocal tract. First, electric voice synthesizer, or some kind of electronic, to be honest, electronic synthesizer. It was introduced and demonstrated on the World Fair This World Fair was held in 1939, before the Second World War, in New York. And they have presented completely electronically implemented synthesizer. It was developed in Bell Telephone Laboratory under name Voder. This Voder is short for voice operated recorder. And at that time, of course, it was some kind of special exhibition, because it was something really completely new. It was invented by a guy working for Bell Laboratory at that time, Homer Dudley. How it looked like, you can see here this exhibition hall, and in the middle is one lady controlling this Voder with this kind of keyboard. So she had a keyboard, and with these keys she was able to control the resonant frequencies of such transfer function that we described here. So with these keys she was able to select which resonant frequency is used for particular sound. Okay? Then at the same time she had a wrist switch. With this wrist switch she was able to select whether the excitation is voiced excitation or unvoiced. Wrist bar, it switches from vowels to consonants or reverse. Then she had additional pedal. This pedal was to change the pitch of the signal, and some pitch control knob to preset some values of the pitch frequency. I will try to reproduce now the actual recording of this system. That was shown on this World Fair. Let me just find this.
Will you please make the voter say for our Eastern listeners?
This is the actual
radio audience
guy. This is the
And
synthesizer.
now for our Western listeners, say good afternoon, radio audience.
Good afternoon, radio audience.
Will you please make the voter say for our Eastern listeners, good evening, radio audience.
Good evening, radio audience.
And now for our Western listeners, say good afternoon, radio audience.
Good afternoon, radio audience.
Will you please make the voter
Okay.
say for our Eastern listeners?
So we
good-
can hear that this is definitely not natural sounding, but is intelligible. So we can understand what this synthesizer is speaking. And for this application, there were, I think, several hundreds of operators were enrolled to this training. And finally, only, I guess, 10 or even less were selected that were capable of doing this in real time, because you had to control all of these keys based on the desired sound you wanted to produce. And to be natural, with a naturally changing pitch, with a naturally changing amplitude, and corresponding excitation that should be either periodic or noise-like. Okay? So there are, if you just in Google write these few keywords, Voder, first synthesis, speech synthesis, then you would find many pages describing this in detail. Okay, so this was the first synthesizer that was based on controlling electronic synthesizer where vacuum tubes, filter circuits, were used to create these resonant characteristics. So the resonant characteristics was controlled with these keys, but it was actually implemented as an active filter using vacuum tubes. Okay, so based on this wrist switch, you selected whether the source of the excitation was random noise for the unvoiced sounds, or for the voiced sounds, if it is a relaxation oscillator whose pitch was controlled with a pedal. So in this case, after selecting the source, you would pass this source to a set of resonant filters, which were controlled with these keys. And finally, it was amplified and passed to the loudspeaker. Okay, so that is the basic idea how this speech synthesis was done and why it was that important at that time. It was 1 year before beginning of the Second World War. And actually, the concept was used for secure communication between allies, US and UK at that time. So the president of the US was able to communicate to the Churchill guy in the UK on a secure channel where this digital information was transmitted as some kind of telegram, and at the receiving side it was reconstructed the same way it is reconstructed here. So it was used for first secure communication, voice-based secure communication for military purposes. The story is it was not used that oftenly because I guess Churchill was not satisfied with the quality of this reconstructed speech, and he decided ignore that, just call him, ignore the security. Okay, so it was not that much applied in the actual situations because at that time it was still of rather low quality. And then based on all of these ideas that were developed at the beginning of in the mid of the last century, 10 years later or 15 years later, when they really had computers, so in the mid-60s, they already have computers, okay? And now we can do all of this stuff not on the analog system that is based on analog vacuum tubes and selective filters. Now we can do all this on computers. We can simulate the operation of such resonant circuits with the algorithm. And in 1966, in Japan, two guys, one is Fumitada Itakura and Saito, I don't know, say something. They proposed the algorithm for speech coding that is based on predictive speech coding while they were working for this entity, and this entity is like a telecom provider at that time, the only telecom provider in Japan, similar as AT&T. So these Bell Laboratories, it was the main telephone provider in the US at that time. Okay, so while working for this entity company, they have developed this first digitally implemented speech coder. And if I take the original image from their paper, the paper was the theoretical consideration of statistically optimal methods for speech spectral density. It was published in internal report number 3107, Electrical Communication Laboratory. It is some kind of internal publication of this entity laboratory. This is the original image from this paper. What shows here is find the correlations. So find R0 to R of P, autocorrelation values. Based on the correlation coefficient, form the system of linear equations. So we can recognize here this system of P linear equation in P unknowns, alpha 1 to alpha P. Then solve this linear system, and they have also introduced or proposed an iterative method that is computationally more efficient than by direct solving of a linear equation with P unknowns. So they have introduced this iterative algorithm for finding the optimal solution. And once you have this optimal solution, you simply plug this coefficient into the reconstruction filter. This here is the reconstruction filter. Here is this excitation source, And if I pass either unvoiced, so white noise, or periodic sequence through this reconstruction filter, I would get something that is very close to the original signal, to the original speech signal. So this here is practically exactly what we have described when discussing how to model the short-term correlation of speech using linear prediction. Okay, this is the block scheme. So I have excitation that is either periodic impulse train with a given period or generator of random white noise. So I select the source, either periodic or unperiodic, depending on the type of the sound. If it is voice sound, periodic. If it is unvoiced sound, unperiodic. I multiply this excitation with a given gain. So this gain captures the information about the varying amplitude of speech signal. And then I pass this excitation through this time-varying digital filter, H of Z. So this time-varying digital filter, so this is this IIR filter with time-varying coefficients. So the coefficients are optimally chosen given number of times per second. For example, 50 times per second or 100 times per second, the coefficients are computed and applied. Okay? And that is the basic of LPC vocoder. So LPC vocoder is a system. It doesn't try to represent the waveform of the speech. It only tries to have the output signal that sounds similar to the original signal. So that is the only criterion. The only criterion is I want to have this X of n that sounds similar to the original sound. Its waveform doesn't have to be identical to the original waveform. It only has to sound similar. And the idea is the following. So you have the actual recorded speech waveform. And if I'm able to estimate the time-varying parameters of the model, if I'm able to estimate the amplitude and the excitation type for each segment of speech, then I would be able to do the inverse, to synthesize artificial speech by varying excitation, by varying the period of periodic excitation, by varying the amplitude, and by varying the characteristics, by varying the coefficients of this digital filter. So in the sense of analysis, the goal is to find this set of parameters and how they change with time. In the sense of synthesis, I apply these estimated parameters and use them to synthesize output speech, which sounds similar to the original signal. Okay? And this kind of model is denoted as parametric source coder, because what is encoded, only the parameters are encoded. I encode the pitch period. It is some integer number. I encode this binary position of the switch. I encode this gain factor as some value, usually in logarithmic representation due to the logarithmic behavior of our perception. Then also I encode the coefficients, individual coefficients, alpha 1, alpha 2, up to alpha p of this reconstruction filter. So these parameters are encoded and transmitted to the receiving side. And on the receiving side, I have the synthesizer that exactly uses this set of parameters, which are changing with time. And what I get synthetic speech. I get synthetic speech. I said all of this. I will now show how this actually works. Simulation of vocoder was done in MATLAB. The actual program was prepared for the laboratory exercises of the course Digital Speech Processing. We have used a sampling frequency of 11 kilohertz, and the analysis window was 46 milliseconds. The analysis step, so I have repeated the analysis 100 times per second by shifting this window, which is 46 milliseconds long, by shifting it by 10 milliseconds. So I have the overlap between two neighboring analysis windows. The prediction order is 12. And this here shows, for example, how this gain factor is varying with time. The sentence I'm uttering, the sentence that I'm speaking, ovo je moj glas. Ovo je moj glas. That is the sentence. You see the higher amplitude once you are uttering vowels. So vowels have larger energy. O, oje, o, a. Consonants have lower energy because they are more or less noise-like and they are of lower energy than the vowels which are periodic. The coefficients, how these coefficients alpha 1 to alpha p change with time, it is shown here. So this curve shows each individual coefficient alpha 1 to alpha 12 as they vary along this pronunciation ovo je moj glas. So I have exactly the parameters of the vocal tract model as a function of time for each sound that I'm producing. And finally, this here shows the period of the excitation signal for the voiced sounds. So, of course, all vowels are voiced. In this case, also V and Y are also voiced consonants. M and Y are also voiced consonant. S is unvoiced consonant. So I don't have any periodicity with S because it is noise-like signal. For all other sounds, ovo je moj glas, I have some periodicity, and the period is shown here in milliseconds. No, in samples. In samples. Period in samples is shown here. And this contour, this curve, shows this natural intonation along pronunciation, ovo je moj glas, ovo je moj glas, something like that. Okay? This shows voiced, unvoiced, voiced, unvoiced, voiced, unvoiced, okay? So which part of the pronunciation is voiced, then unvoiced, voiced, unvoiced, okay? It ends up with this S, which is unvoiced. The same is shown as a wideband spectrogram. So for the same sentence, we see the formants. First formant, second formant, here, maybe here, third formant, here, 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 fourth formant, somewhere around here, okay? So this is the wideband spectrogram. And this is wideband spectrogram of synthetic signal, of synthesized speech. So this is the original speech, and this is synthetic speech. So you see that this wideband spectrogram is more or less similar in both cases. So I have retained all of the format structure that was present in the original signal. And now, how does it sound? Now I will try to reproduce how does it sound. Window. Okay. D, empty. Okay, so this is the original.
Ovo je moj glas. Ovo je moj glas. Ovo je moj glas. Ovo je moj glas.
So this is the original. And synthesized speech is this one.
Ovo je moj glas. 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 Ovo je moj glas.
You can hear it is slightly different. So there is some artifacts of this modeling that are hearable. You can really hear these artifacts, but nevertheless, this is completely intelligible. You could understand what one is talking. Once I have such a model, I can also easily manipulate